Hello everyone, welcome to our channel, Hidden Rees. In this video, we will be discussing how our planet Earth was formed, from its beginnings as a cloud of gas and dust to the dynamic and diverse planet we know today. So, grab a seat and let's dive into the history of our planet. The formation of Earth began about 4.5 billion years ago, during the early stages of the solar system's creation. At this time, a cloud of gas and dust was swirling around a young, hot star. Over time, this cloud began to condense, and the force of gravity pulled the particles together, forming a protoplanetary disk. As this disk continued to evolve, the particles within it began to clump together, forming larger and larger bodies. These bodies eventually became the planets of our solar system, including Earth. However, Earth's formation was not a simple process. The formation of Earth. Earth's formation can be divided into several stages. The first stage was the formation of a small, rocky planetesimal. These planetesimals were formed from the collisions of smaller particles within the protoplanetary disk. Over time, these planetesimals continued to collide and merge, forming larger and larger bodies. Eventually, these bodies grew to be large enough to start attracting gas and dust from the protoplanetary disk. This gas and dust then collapsed onto the surface of the growing planet, adding to its mass and causing it to become even more massive. This process is known as accretion. As the planet continued to grow, it began to heat up due to the energy released by the collisions and the gravitational forces at work. This heat caused the planet to differentiate, with heavier elements sinking to the core and lighter elements rising to the surface. Another important factor in the formation of Earth was the presence of Jupiter. Jupiter is the largest planet in the solar system, and it has a strong gravitational pull. This gravitational pull helped to shape the orbits of the planets and prevented them from colliding with each other. Without Jupiter, the inner planets would have been more susceptible to collisions, which could have altered their orbits and made it less likely that Earth would be in the habitable zone. The early Earth. As Earth continued to form and evolve, it was a very different place than the planet we know today. The early Earth was a hot, molten planet, with a surface covered in volcanoes and no atmosphere to speak of. However, over time, the volcanic activity on the planet began to release gases into the atmosphere. These gases included water vapor, carbon dioxide, and nitrogen, among others. As the planet cooled, these gases began to condense and form an atmosphere. This atmosphere was very different from the one we have today. It was rich in carbon dioxide and nitrogen, with very little oxygen. However, over time, photosynthetic organisms began to evolve, producing oxygen as a waste product. This oxygen then began to build up in the atmosphere, eventually leading to the formation of the ozone layer, which protects us from harmful solar radiation. The magnetic field of Earth. Earth's magnetic field is generated by the motion of molten iron in the planet's core. As the Earth rotates, the molten iron in the outer core moves in a circular pattern, creating a dynamo effect that generates the magnetic field. The process by which the magnetic field was established in the early Earth is not fully understood, but it is believed to have been created during the formation of the planet as the molten iron in the core began to move due to the heat generated by the planet's accretion. As the planet continued to cool, the solidification of the core caused the magnetic field to become more stable and long-lasting. The magnetic field has played a crucial role in the evolution of the planet, protecting it from harmful solar radiation and maintaining its atmosphere and climate. In fact, our Earth is not big as now. Then how the Earth got this size? The main reason for the size of Earth is got from during the formation of Moon. The Moon has been a constant companion to Earth for billions of years, but how did it come to be? The leading theory is that the Moon formed from debris left over after a Mars-sized object collided with Earth early in the planet's history. This theory, known as the giant impact hypothesis, was first proposed in the 1970s by scientists William Hartmann and Don Davis. According to the hypothesis, a Mars-sized object, which has been named Theia, collided with Earth about 4.5 billion years ago, when the solar system was still forming. The impact was so violent that it ejected a large amount of debris from both Earth and Theia into space. The debris from the collision eventually coalesced to form the Moon. This process is called accretion, and it involves the gradual buildup of material into larger and larger bodies. The Moon formed relatively quickly, in a matter of tens of thousands of years, as the debris coalesced in orbit around Earth. The giant impact hypothesis explains several key features of the Moon. One is the similarity in composition between the Moon and Earth's mantle, which is the layer of rock that lies beneath the planet's crust. This suggests that the Moon formed from material that was once part of Earth. Another piece of evidence in support of the giant impact hypothesis is the Moon's orbit around Earth. The Moon's orbit is relatively stable, and it is locked in a synchronous rotation with Earth, which means that the same side of the Moon always faces Earth. This is thought to be the result of gravitational interactions between the two bodies during the Moon's formation. The giant impact hypothesis is also consistent with the fact that the Moon is relatively large compared to Earth. The Moon is about 1/4 the diameter of Earth, which is larger than the typical ratio between a planet and its Moon. This suggests that the Moon formed from a larger amount of debris than is typical for a moon-forming event. While the giant impact hypothesis is the leading theory for the Moon's formation, there are still some questions that remain unanswered. One of these is the issue of the Moon's angular momentum. The Moon has an angular momentum that is much larger than would be expected from the giant impact alone. This suggests that there may have been additional processes at work, such as a resonance between Earth's rotation and the Moon's orbit, that helped to increase the Moon's angular momentum. Despite these remaining questions, the giant impact hypothesis remains the best explanation for how the Moon came to be. It is a testament to the dynamic and violent history of the early solar system, and it has had a profound impact on Earth's evolution. The Moon has played a key role in stabilizing Earth's rotation and climate, and it has inspired countless myths, legends, and scientific discoveries. The Earth and habitable zone. Earth is a remarkable planet in many ways. It is the third planet from the Sun, and it has a number of features that make it unique in the solar system. One of the most important of these features is its location in the habitable zone of the Sun. The habitable zone, also known as the Goldilocks zone, is the region around a star where conditions are just right for the existence of liquid water on the surface of a planet. This is important because water is a key ingredient for life as we know it. Too close to the star, and the water would evaporate. Too far away, and it would freeze. Earth is located in just the right place to have liquid water, making it a prime candidate for the emergence and evolution of life. The habitable zone around the Sun extends from about 0.95 astronomical units, to 1.37 astronomical units. 1 astronomical unit is the distance between Earth and the Sun, which is about 93 million miles. Earth's orbit around the Sun is approximately 1 astronomical unit, which means it is just within the inner edge of the habitable zone. Earth's location in the habitable zone has had a profound impact on the evolution of life. The presence of liquid water on the surface of the planet has made it possible for life to emerge and evolve. The first living organisms on Earth were simple, single-celled organisms that lived in the oceans. Over time, more complex life forms evolved, including plants, animals, and eventually humans. The habitable zone is not a fixed boundary, and it can vary depending on the properties of the star. For example, a star that is smaller and cooler than the Sun would have a habitable zone that is closer in. Conversely, a star that is larger and hotter than the Sun would have a habitable zone. How Earth got water. Water is essential to life as we know it, and Earth is the only known planet in our solar system with large bodies of liquid water on its surface. But how did Earth get its water? The answer to this question is a fascinating story that involves both the formation of the planet and the delivery of water-rich materials from space. During the early stages of Earth's formation, the planet was bombarded by a steady stream of asteroids and comets. These impacts brought water-rich materials to Earth, including water molecules trapped within the minerals of the asteroids and comets. Some of these impacts were so violent that they melted the surface of the planet, creating a magma ocean. As the magma cooled, water vapor from the impacts was able to condense and form liquid water on the surface. But the delivery of water-rich materials to Earth was not the only factor in the planet's water abundance. Earth's distance from the Sun also played a crucial role. Early in the planet's history, Earth was much hotter than it is today, and much of the water that was delivered to the planet would have been lost to space through a process known as atmospheric escape. However, Earth's position in the habitable zone of the Sun allowed it to retain enough of its water to eventually form oceans. Another source of Earth's water may have come from within the planet itself. As the planet continued to form and differentiate into layers, water-rich materials may have been trapped in the lower layers of the mantle. These materials may have been brought to the surface by volcanic activity, where they were able to form the oceans and other bodies of water we see today. Overall, the origin of Earth's water is a complex and multifaceted story that involves both the formation of the planet and the delivery of water-rich materials from space. Without this water, life as we know it would not be possible on Earth. It is a reminder of the interconnectedness of the universe and the profound role that water plays in the story of our planet. The Earth today. Today, Earth is a dynamic and diverse planet, with a wide range of ecosystems and a complex atmosphere. It is the only planet in our solar system known to support life, and it is home to millions of species of plants and animals. The planet's surface is constantly changing, with the forces of weathering, erosion, and plate tectonics shaping the landscape. These forces have created some of the most spectacular geological formations on the planet, from the Grand Canyon to the Himalayas. That's it for the today. From this video you got the great experiences about our own planet formation where we living, and these events of the formation gives more responsibility to the human beings. Because, humans have a significant impact on the Earth and its ecosystems. From industrial activities to urbanization and agriculture, human activities have led to deforestation, climate change, pollution, and other environmental problems. One of the most significant ways that humans are impacting the Earth is through the emission of greenhouse gases, primarily from the burning of fossil fuels for energy. These emissions are causing the Earth's temperature to rise, leading to a wide range of environmental problems, including more frequent and severe weather events, melting ice caps, and rising sea levels. Ultimately, it is the responsibility of all humans to take care of the Earth and ensure that it remains a healthy and hospitable planet for future generations. And also, Earth is not only for the human beings. It is the planet for all organisms.